Welcome back to the deep dive. Today we're opening up a file that it feels a little bit like finding a secret tunnel underneath a massive fortress.
That's a great way to put it, honestly.
Because we're talking about the absolute heavyweights of the modern world. You
Right.
know them, you probably talk to them every single day.
Right, ChatGPT, Claude, Llama.
Exactly. These are the undisputed kings of the hill.
They certainly are. I mean, they've completely revolutionized how we interact with technology, how we code, how we write. It's the era of the large language model.
But, and there is always a but on this show, there is a massive hidden cost to these kings. I was reading through the research today, and it turns out the engine that runs all these models, the famous transformer architecture, it has a flaw.
Yes. Mathematical ceiling,
Right.
it's what we call the quadratic bottleneck, and it's a huge problem if we want AI to keep getting better and faster and handling more information.
So today we are diving into a paper that claims to have found a loophole, a way to basically smash that ceiling. The paper is from 2023, and it's titled RWKV, Reinventing RNNs for the Transformer Era. And the mission here is wild.
It really is.
They want to combine the best of the old school with the best of the new school. Essentially, they're trying to build a model that learns as fast as a transformer, but runs with a fraction of the memory.
It's a fascinating attempt to reconcile two rival technologies. Because on one side, you have the parallel training speed of transformers.
Which is why we have such smart AI today.
Exactly. And on the other side, you have the efficiency of recurrent neural networks, or RNNs, which were the old standard. So RWKV wants to be a model that is just as smart as a transformer, but infinitely lighter to run.
It sounds like trying to put a Ferrari engine inside a bicycle just to get the best gas mileage in the world.
Pretty much.
So before we get into the how, let's unpack this battle of architectures. We've got the old guard, the RNNs, and the current kings, the transformers. Set the scene for us. Why did we ditch the old guard in the first place?
Well, recurrent neural networks, RNNs, they operate on a very intuitive principle. They process text sequentially, word by word.
Okay.
Imagine you're reading a book. You read the first word, update your mental state, then you read the second word, update again, and so on. It's a relay race.
Right.
You can't start the second leg until the first runner hands off the baton.
So step one, then step two. Very human.
Precisely. And because of that, they are incredibly memory efficient. Their memory usage scales linearly. If you double the length of the text, you essentially just double the work.
Which is super manageable.
Very manageable. But there was a major issue. Because you have to finish step one before you can start step two, you cannot parallelize the training.
Ah, you can't just throw 1,000 GPUs at it and tell them all to work at once.
Exactly. You're stuck in this slow, single-file line. Plus, RNNs suffered from something called vanishing gradients.
Vanishing grading.
Basically, by the time they got to the end of a long paragraph, they'd forgotten what happened at the very beginning. They just couldn't hold on to the context.
Right. It's like when I start telling a story and get totally sidetracked, and by the end, I have no idea why I started talking in the first place.
Yeah.
The signal just fades out.
A very human problem, yes.
Yeah.
So in 2017, the transformer arrives. And the transformer changed the game because it uses self-attention.
Okay.
Instead of reading word by word like a relay race, it looks at the entire sequence all at once. It compares every single word to every other word to figure out the context.
Which means you can train it in parallel. You can throw all the compute in the world at it, and it learns incredibly fast. That really explains the explosion of AI we've seen recently.
It does. But here is the cost we mentioned earlier. That mechanism comparing every word to every other word is quadratic.
Okay, let's unpack quadratic, because it sounds like high school math class, but the implications are actually pretty wild when you think about it.
They are.
I was trying to visualize this. It's almost like a networking event. If an RNN is at a party, it meets person A, shakes hands, then meets person B, shakes hands, linear work. Very easy.
Right. Simple one-to-one interactions.
But a transformer. Every time a new person walks into the room, they have to go shake hands with everyone who is already there.
Yes.
And everyone who is already there has to shake hands with them again to update their context.
Is a fantastic analogy, and the math backs it right up. If you double the number of people, or words, the amount of handshakes doesn't just double, it quadruples.
Wow.
If you increase the length by 10 times, the computational cost goes up 100 times. It's O of t squared.
And that is exactly why, if you're using ChatGPT and the conversation gets really long, you can almost feel the server sweating.
It's why there's a strict limit to how much text you can paste into those prompt windows. The memory requirement essentially goes vertical on a graph. It just becomes unsustainable.
So enter RWKV. The paper says it's reinventing RNNs. How does this model manage to be both things at once? I mean, how can it be a transformer and an RNN?
It sounds like a total paradox, doesn't it? But the authors pulled off a really elegant mathematical trick here. They designed the RWKV model to have a dual identity.
A dual identity.
Yeah. During the training phase, the math is formulated so it can be parallelized, just like a transformer. So it learns fast and scales up on those massive clusters of GPUs.
Okay, so the engineers are happy because they can train it quickly. It trains like a king.
But once it's trained and you're actually using it what we call inference, it switches modes. It can be formulated mathematically as an RNN.
Oh, I see.
It runs sequentially.
Yeah.
It doesn't need to look back at the whole history of every handshake at the party. It just needs the state from the previous step to calculate the next one.
So it trains like a transformer, but runs like an RNN.
That is the best of both worlds claim they're making.
All right, let's pop the hood then. RWKV. It's an acronym. What exactly are we looking at here?
It stands for receptance, weight, key, and value. Now, key and value are terms borrowed straight from the transformer world, but receptance and weight are the new twists here.
And the secret sauce is something they call linear attention, right?
Correct. Traditional transformers use dot product attention. That's that expensive, compare everything to everything matrix. RWKV uses a linear attention mechanism. Instead of a massive matrix, it uses channel-directed attention. But the real magic is in the W, the weight.
The weight. Now, this connects to that vanishing gradient problem you mentioned earlier, right? The issue where RNNs forget things over time.
It does. RWKV introduces a positional weight decay vector. Think of it as a tunable dial for memory. In the old RNNs, information just naturally faded away, and often way too fast. With the W parameter, the model actually learns how to forget.
Learning how to forget? That sounds weirdly poetic.
It's incredibly practical. It learns mathematically that some signals need to decay slowly, staying in memory for a long time, and some should decay instantly because they just aren't important.
Right.
It creates a balance. It allows the model to maintain relevant information over long distances without needing to keep a perfect, pixel-perfect copy of the entire history in its active memory.
So instead of just blindly forgetting everything after a while, like the old models, it's doing active memory management.
Exactly. And this leads directly to that dual identity. The paper gets pretty technical here, but the gist is that they found a mathematical way to rewrite the equation.
How so?
Well, in time parallel mode, which they use for training, the equation looks exactly like a transformer. You can compute all the time steps at once. But in time sequential mode, for chatting with it, it's recursive. You calculate step t using only the info from step t-1.
And the efficiency stats in the paper are just mind-blowing. They claim constant computational and memory complexity during inference.
Constant. That is the key word here. Whether the conversation is 100 words long or 10,000 words long, the amount of RAM you need to generate the next word is exactly the same.
That is a massive difference from transformers, where the RAM usage would be exploding right off the chart.
It changes the economics of running these models entirely.
Okay, but here's my skepticism check. Theoretical efficiency is great on paper, but usually when you strip out the heavy machinery of a transformer, the model gets, well, it gets stupid.
Right.
Does RWKV actually work, or is it just a really fast model that speaks gibberish?
That is the big question.
Yeah.
And the authors didn't just write a theoretical paper. They actually scaled it up to prove it. They trained models ranging from 169 million parameters all the way up to 14 billion parameters.
Wow, 14 billion is no joke. That is a serious production-level large language model.
It is. They trained it on the pile, which is a massive standard data set for these things, basically a huge curated chunk of the internet, and they pitted it against similarly sized transformers, specifically models like Pythia, OPT, and Bloom.
And the verdict?
It's surprisingly good. On standard NLP benchmarks, tests like RC for reasoning, HelloSwag for common sense, PIQA RWKV performs entirely on par with the transformers.
On par is a very strong statement.
It is. They include a graph in the paper, plotting accuracy against compute. And the RWKV line sits right alongside the transformer lines. You essentially cannot tell the difference in performance for a given amount of training.
So you're not paying a stupidity tax for the efficiency.
According to these benchmarks, no. And when you look at the inference experiments, that's where RWKV really starts winning. They show that as sequence length increases, the transformer memory usage goes vertical. It skyrockets. But RWKV's memory usage is just a flat line.
And what about speed?
Significantly faster for long contexts. because it's not doing that quadratic cross-referencing. That handshake with everyone at the party generating text doesn't get slower the more you type.
This sounds almost too good to be true. We have a model that's just as smart, trains just as fast, but runs infinitely cheaper and faster. There has to be a catch. We need to talk about the trade-offs.
There's always a trade-off. There is no free lunch in computer science, and the paper is quite honest about this in their limitations section. It really comes down to the fundamental difference between a state and a history.
State versus history. Break that down for us.
A transformer keeps the history. It has the raw data of every single token it has ever seen in the current context. It can look back at word number 5 when it's generating word number 5,000 with absolute perfect clarity.
Like having a photographic memory of the entire conversation, or having the actual book open right in front of you.
Exactly. RWKV, being an RNN at heart, keeps a state. It compresses all that history into a single vector representation.
Yeah.
It's essentially a summary.
Ah, okay. I see where this is going. If I read a book and take incredibly detailed notes, I have a great state. I understand the plot, the characters, the themes.
Right. But if I ask you what was the third word on page 45, you can't tell me. Your notes, your state didn't capture that specific tiny detail because it just didn't seem important at the time. A transformer, however, basically has the book open to page 45 and can just look.
So RWKV might struggle with tasks that require perfect recall of some random detail from 5,000 words ago.
Exactly. The paper explicitly admits this. They say this limits the ability to recall minutiae information over very long contexts. If the model didn't think a detail was important when it first saw it, that detail might be totally lost from the state. It has decayed.
And this leads to one of the most fascinating parts of the paper for me, the section on prompt engineering, because this inability to look back fundamentally changes how you have to talk to the model.
It does. They found RWKV is very sensitive to the order of the prompt.
They gave this great example of a task called RTE, recognizing textual entailment. Basically, figuring out if one sentence logically follows another.
Right. Now, with transformers like GPT-4, we've gotten a bit lazy. We usually just paste the question first. We say, does this make sense? And then we paste the massive long text or context below it.
Because the transformer sees it all at once anyway, so the order doesn't really matter. It can just hop around the text.
Correct. But when they used that standard prompting style with RWKV, it scored poorly. It scored something like 44.2%.
44.2% is basically guessing. That's a fail.
It is. But they realized the problem. Since the model processes sequentially and can't look back easily, by the time it reads the massive context at the end, it might have decayed the specific nuances of the question it saw at the very start. The signal just faded.
So they flipped it.
They reordered the prompt entirely. They put the context first and the question last.
Adapting to the linear nature of the RNN. Here is the story, now here is the question.
And the score jumped from 44.2% to 74.8%.
That is a massive jump. That's almost a 30% increase in measurable intelligence,
Right.
just by moving the paragraphs around.
It really highlights a crucial difference. With transformers, we treat the prompt as a bucket we just throw words into. With RWKV, you have to think about the flow of information. You have to feed the information in a way that updates the internal state correctly so that when the question finally arrives, the brain is ready to answer it. You have to prime the state.
It's almost more human in a way. I mean, if you ask me a really complicated question and then read me a 10-page essay, I'm going to spend the whole time reading the essay just trying to remember what on earth you asked me in the first place.
That's a very fair comparison.
But if you read me the essay and then look me in the eye and ask the question, I'm ready. I have the context loaded.
Exactly. It shows that reasoning capability is sometimes just a matter of information flow.
So we have a model that requires a bit more care in how you talk to it, but it offers these massive efficiency gains. Why does this matter for the bigger picture? If you're listening to this, why should you care about RWKV?
I think the biggest implication is democratization.
Democratization? How so?
Right now, running a top-tier LLM requires massive data centers with thousands of dollars worth of VRAM. It's centralized power. RWKV's efficiency, specifically that low VRAM usage, makes running high-performance LLMs on consumer hardware much more feasible.
We're talking about running a 14 billion parameter model on a gaming PC or maybe even a high-end phone.
Exactly. Because the memory usage doesn't grow with the conversation, you don't hit that wall where your computer crashes just because you talk to it for too long. This opens the door for personal AI assistants that run locally, privately, on your own device, without sending your data to a cloud giant.
That is huge for privacy. And for people who don't have $1 million for a server farm, it feels like taking the power back a little bit.
And there's another aspect too, long contexts. We always want our AIs to remember more. So they did an experiment called extended context fine-tuning.
Oh, this was cool. They took a model trained on 924 tokens, which is pretty short, and taught it to handle longer sequences.
Yes, they showed they could fine-tune it to handle 192 tokens efficiently. And because the linear scaling, doing this fine-tuning didn't cost a fortune.
Right.
Trying to fine-tune a transformer to suddenly handle 8,000 tokens is incredibly computationally expensive because of that quadratic cost we talked about.
So RWKV could essentially be the architecture that finally gives us AIs that can read entire novels or massive code bases without breaking the bank.
That's the hope. It opens the door to effectively infinite context as long as you have the time to process it sequentially.
And one final thing that's really interesting for researchers is interpretability. You mentioned this earlier, the idea of looking inside the brain of the AI.
Yes. With transformers, the thought process is usually a total black box. It's scattered across that massive attention matrix where everything is connected to everything. It's very hard to say, why did it think that?
But with RWKV?
Because RWKV passes a state from one step to the next, you can actually see what information is moving through the channels. They did this Eiffel Tower experiment.
Right. They asked it about the Eiffel Tower being in Paris.
And they could trace the information flow layer by layer. They could pinpoint exactly where the model recalled Paris after seeing Eiffel Tower and how that information moved through the layers to the final output. It was in layer 4, essentially, that the retrieval happened.
That is wild. It's like being able to watch the actual neurons fire in sequence.
It offers a window into the black box that we just don't usually get. It can be huge for AI safety and truly understanding how these things actually reason.
So, wrapping this up, RWKV represents a best of both worlds attempt. The training speed of the modern era, but the runtime efficiency of the classic era. It's 14 billion parameters of proof that we don't have to stick with the transformer architecture forever.
It's a very strong signal that the transformer isn't the end of history for AI. It's not the final form. There are more efficient ways to build these brains. RWKV is proving that you can have intelligence without the massive computational bloat.
It really makes you think. We look at these leaderboards and say, Model A is smarter than Model B, but looking at that prompt engineering example where reordering the words changed the score by 30%, it leaves me with a burning question for everyone listening. Are we actually measuring reasoning capability, or are we just measuring how well a model has memorized the specific sentence structures that transformers prefer? If you speak transformer language, the model seems like a genius. But if you speak RNN language, the transformer might look dumb, and RWKV looks like Einstein.
That is the ultimate question. We might just be measuring how well we fit the tool rather than the intelligence of the tool itself.
Definitely something to mull over the next time you're trying to get a straight answer out of a chatbot. Thanks for joining us on this deep dive into RWKV. We'll see you all next time.